Hey everyone, let's get started reviewing Chapter 5. Number 1, find the probability using the standard normal distribution. The probability that your z-score is less than 1.49. Okay, well, if we're talking about the standard normal distribution, that means that all the x values have been standardized. They've been turned into z-scores, and we know that the mean right in the middle of our standard normal distribution is a z-score of 0. So any positive z-score, especially if we're talking about 1.49, would be somewhere to the right here. And if I want to find the probability of being less than that value, that means I'm really looking at the area that is being shaded to the left of 1.49. Okay. Now I want to go through, some calculator directions with you. You can do this on the calculator. There is a way to find this area using a function on the TI-84. The most obvious way is to use the z-score table that's in the textbook. So I would be looking up 1.4 on the positive side of my z-score table. And then I would be scrolling across the columns to where it says 0.09. So 1.49 would be 0.9319. So that would be A. Okay. Another way to go about this on the calculator would be through the distribution menu. So we're going to hit second, the variables button. And then you want to click normal CDF, normal cumulative density function. So we're going to scroll down to number 2. And if you have a newer calculator, there's usually a menu that pops up here that you could put in your left bound, your right bound, your mean, and your standard deviation. I have an older calculator, so I have to put these in manually. I would say that I want to go from as far left as I possibly can, because remember this graph never actually touches the x-axis, so it continues forever and forever this way. So I want to go as low as like negative 10,000, right? This is going off forever and forever in the leftmost direction. So I'm going to say negative 10,000 as my lower bound. My upper bound, the area here that I have shaded is stopping up here at the 1.49. And then the mean, well, we're talking about the standard normal distribution, so the mean here is 0, and the standard deviation is 1. And then we close parentheses, and there again we get the 0.9319. Okay, so you can use the table, the z-score table, or you can use the normal CDF function, which is, again, you want to do the lower bound, then your upper bound, then your mean, and then the standard deviation. Those are going to be the 4 inputs into that function in order to come up with the area shaded under the curve. Number 2, find the probability using the standard normal distribution, the probability that the z-score is greater than negative 2.31. Okay, so we're going to go through this again. We're on the standard normal curve. I know the middle z-score there is 0. My standard deviation is 1. I want to figure out how I can be greater than negative. Well, if I'm negative, I'm down here to the left. Negative 2.31, and I want to be greater than that. Well, that means that I am shading area to the right of that curve. So all of this area here. Okay. So if I'm using the table, you do have to be a little bit more conscientious when you're using the table, because it only gives you values that are areas shaded to the left. So since this is an area that's shaded to the right, whatever number I come up with looking at the table, which in this case I got to look at the negative side, negative 2.3, and then I'm going to scroll over my columns until I hit the 1. And that gives me 0.0104. That's this number right here, 0.0104. That's that area. The area in the table is always assuming area shaded to the left. So if I want to figure out this area, that means I have to do 1 minus the value that I come up with in the chart. So I'm going to do 1 minus 0.0104, and that's going to be 0.9896. That's C. Now again, if I'm doing this on the calculator, not with the table, second the variables button gets me into distributions. I want the normal CDF. My lower bound here is I'm starting at negative 2.31. And I'm going off forever and forever in this direction. So I'm going off to like positive 10,000. You just want to pick a really big number, right? Because eventually this area that's trapped underneath the curve, gets pretty negligible once you get out so far. So you just want to pick a really big value. And then 0 for the mean, 1 for the standard deviation, close parentheses, and there we get the 0.9896 again. Okay, so just a little calculator work there, practicing finding area trapped under the standard normal curve. Number 3, find the probability using the standard normal distribution. Here we're finding area that is trapped between z-scores. So if I were to physically draw this picture, here's my standard normal curve with a mean of 0, standard deviation of 1. I want to find the area trapped between a negative 2.14 and a positive 0.95. Okay, area trapped between here. Okay, so I'm finding this area right here. If I'm using my table, this is just a simple subtraction problem, so I'll just highlight here real quick. When I look up the value for 0.95, it's going to give me all of this, right? Everything that is below 0.95. If I look up the area that's associated with negative 2.14, that's going to give me this area. So if I subtract what I have shaded in green from what I have shaded in yellow, I'm going to get that orange in between area that I want. So looking this up on the chart, I'm going to start on my positive side first because that's going to be the bigger area. 0.95 is 0.8289. 0.8289. Did I say that right? Yeah. My smaller area that's in green there is going to be on the negative side. Negative 2.14, negative 2.1, scroll over to the 4.0162, 0.0162. If I subtract those two areas, I should find the area that is in between, 0.8289 minus 0.0162, 0.8127. I should get D. Now practicing on the calculator again, second the variables button, normal CDF, I'm trying to find probability of the normal distribution, the cumulative density function. My left bound here is going to be the lower z-score, negative 2.14. The right bound, or the upper bound, is going to be the 0.95. And then we're going to put in the mean, we're going to put in the standard deviation, close our parentheses, and again, we get the 0.8127. Alrighty, let's continue with number 4. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the probability a randomly selected person has an IQ score greater than 120. Okay. So in this situation, it's not standardized yet. We're just told that IQ scores are normally distributed, and their mean is at 100 and the standard deviation is at 15. So if I want to find the probability of getting just a random person that has an IQ greater than 120, 120 would be up here somewhere above the 100, and being greater than that would be assuming area shaded to the right. Okay. Now, the reason that I can't rely on the empirical rule, the 68, 95, 99.7 rule, is because the standard deviation markers are not falling on this IQ score that I'm curious about, right? The first standard deviation marker would be at 115. That's one standard deviation above. Two standard deviations above would be at 130. And then the next one would be at 145, right? So 120 does not fall nicely on any of those standard deviation markers, so I can't assume the empirical rule. It's not really useful to me. So the only thing I can do is standardize this score using my z-score formula. X minus the mean, so the data value, minus the mean divided by the standard deviation. So in this case, the standardized IQ score of 120 will be found with this formula. So 120 minus 100, well, that's going to be 20 divided by 15. The standardized score is approximately 1.33. Now, I could either look that up in the body of the table, right, which would give me this area. It would give me that percent, and then I would have to subtract it from 1 to figure out the area above, or I can use that normal CDF function. So I'm going to do that. Second the variables button, normal CDF. Lower bound is going to be my standard score of 1.33. We're going to go up to 10,000, something real big. And then we are going to put in 0 and 1 because we have standardized that value. And we're looking at 0.0918. So that would be B. Number 5. Same situation, IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the probability a randomly selected person has an IQ between 100 and 120. Well, I just figured out that the z-score for 120 was 1.33, right? And if the mean is 100 and I'm looking to find the proportion, or percentage of people that are between 100 and 120, that's going to be this area right in here. Well, the z-score for the middle value is going to be 0, right? Because it's the mean. So I'm going to plug that back into the normal CDF again. But this time going from 0 to 1.33. .4082. That's going to be C. All right, number 6. Find the z-score. Find the z-score that has 2.68% of the distribution's area to its right. Okay. All right. So I'm looking for the z-score that has 2.68% of the distribution's area to its right. Now, how do I know to put the z-score all the way up here? Well, 2.68% is not very much. I know it's going to be a very small area somewhere above the line of symmetry that this z-score is going to be if there's only 2.68% of its distribution to its right. There's a couple ways we could go about doing this. I could come up with the area that is left of this value, right? I could come up with what I have shaded in green here, not colored in super well, but you get what I'm saying here. I could come up with that by doing 1 minus 0.0268. 1 minus that 2.68% would tell me that the area left of the z-score would be 0.9732, and then I could look up this value in the body of the table. Okay. I could look up this number in the body of the table. All right, here's the z-score table. You've got numbers here, you've got numbers at the top. I would be looking up 0.9732 in the body of the table and then backtracking to find the actual z-score, right? The first two digits and then that hundredths place. Or there is also a function on the calculator that will backtrack areas for you. It's called the inverse norm. It's also in that distribution menu, second the variables button. It's the third option down, INVNORM, inverse norm. And then you just want to put in that value, 0.9732. 1.93 D. 1.93. Okay, so two options there, inverse norm or look up that leftmost area below the z-score. Look that up in the body of the table. We're backtracking to find the z-score. Number 7, IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What IQ score? Okay, now notice this is asking for a data value, not the z-score. What IQ score, what data value represents the 98th percentile? Anytime you see percentile, assume that that means cumulative area. So, right, if the middle is like the halfway point, accumulating 98% means that I'm up here somewhere. I'm way over the halfway point. I've almost got the entire graph shaded in. So we're going to assume that that shaded area is 0.98. So I want to do this inverse norm function again to figure out the z-score that is trapping 98% to the left, which would be about 2.05. Now, that's obviously not the answer. That's the z-score that is doing that. I want to figure out the IQ score that has a z-score of 2.05. And that is easy enough just by algebraically manipulating the z-score formula. If I want to get x by itself, I'm going to multiply the standard deviation over. And then to get x by itself, we're going to add the mean over. So we're going to have z times sigma plus mu is going to be our x value. This is what I'm solving for this time. I'm taking the z-score and backtracking to find the IQ score that would have 98% of the distribution to its left. So we're going to do 2.05, the z-score, times our standard deviation of 15, and then we're going to add 100 to it. So 2.05 times 15, and then we're going to add 100. So 130.75, that's going to round to 131. Number 8, a population has a mean of 80 and a standard deviation of 12. Samples of size 36, sample size is 36, are selected from the population. Describe the sampling distribution of sample means. Okay, so that means we're taking repeated samples of size 36 from some population. Now, notice it doesn't say here what the distribution of the population looks like. It could be anything. It could be any shape. The only thing I know about the population is that it has a mean of 80 and a standard deviation of 12. That's all I know. But I have at my disposal something called the central limit theorem, which comes in two parts. Part 1 tells me that even when I don't know what the population's distribution looks like, as long as I am taking samples that are greater than or equal to 30, I can assume that the sampling distribution of sample means is going to be approximately normal with a mean that is equal to the population mean and a standard deviation that is equal to the population standard deviation divided by the square root of n. So right away, I already know that this is going to be 80, the mean of the sampling distribution. I just need to figure out what the standard deviation of the sampling distribution is going to look like. I know it's going to be approximately normal, so it's either going to be C or D here. I just need to figure out sigma sub x bar. So we're going to take 12 and divide it by the square root of 36. Well, the square root of 36 is 6, so 12 divided by 6 is going to be 2. That narrows it down to C. Number 9. American children watch an average of 25 hours of television per week. Whoa, that's a lot. With a standard deviation of 8 hours. A random sample of 40 children is selected. N is 40. What is the probability the mean number of hours of television they watch per week is less than 22? This right here, this is something you want to flag whenever you're doing problems in my math lab. As soon as you find the phrase or see the phrase probability that the mean, it's asking for a probability of a particular average. This is when you want to make the connection that we're talking about the probabilities in a sampling distribution. Now, this is a little bit different than just the regular probabilities of a standard normal distribution because our z-scores are not just regular data values that have been standardized, they are averages that have been standardized. So in this case, we're taking the sample average in question minus the sampling distribution's average, and we're going to divide that by the sampling distribution's standard deviation, which isn't just sigma, it's sigma divided by the square root of n, right? So again, this is we're doing this whenever we see this phrase about the probability of an average, of a mean. That means we're finding probabilities not just in any old standard normal curve, we're talking about finding probabilities in a sampling distribution, right? So what's the probability that the mean is less than 22? Okay, well, I already know that the average is 25. So I want to figure out what is the probability that it is less than, well, this is 25. 22 is going to be down here. And being less than 22 means that I'm going to be shading area to the left. Okay, so really this question is asking me to find that area because that's going to be the probability. Well, I want to standardize this number of hours. So our z-score is going to be 22 minus 25 divided by the population standard deviation is 8. And we're taking a sample size of 40. So we're going to divide that by the square root of 40. So let's put this in the calculator. 22 minus 25 divided by 8 divided by the square root of 40. Okay, that's our z-score, negative 2.37. Okay, now I need to figure out the area that is trapped by the z-score, negative 2.37. So we're going to do second distribution, the normal CDF, negative 10,000, all the way up to negative 2.37. Everything's been standardized, so we use 0 and 1 for our normal distribution, and that's going to leave us with B, 0.0089. Okay, last question, number 10. Use a correction for continuity to convert the following interval to a normal distribution interval. Okay, correction for continuity. The only time you ever do this, which is again just putting that little bit of wiggle room around the interval, adding 0.5 or subtracting 0.5, the only time you ever do this is when you have a binomial probability distribution and you're approximating it using the normal curve, which means you've already gone through the checkpoints. N times P is greater than or equal to 5, N times Q is greater than or equal to 5. You've gone through this problem and you've decided that this binomial situation can be approximated by something that is normal. Whenever we do this, remember binomial things are discrete. So if it turns out that it is approximately normal, that means we're taking it from a discrete sense to a continuous sense. To do that, I've got to give a little bit of grace, a little bit of wiggle room. That's what we're calling this correction for continuity, going from something that is discrete to continuous. So in this case, let's think about what it's asking. The probability of getting at least 80 successes, at least 80. At least 80 means 80, 81, 82, so on and so forth. All of those numbers are at least 80. Well, if I want to capture 80 in the normal sense, if I want to capture 80 using this continuous normal curve, that means I need to go a little bit left of that value, so I make sure I actually capture that value. So my continuity for correction is going to be half a unit left of 80, which means that I'm going to start down at 79.5 in the continuous sense. So I think that is going to be B. X is greater than or equal to, greater than because we're continuing to the right here, 80, 81, 82, greater than 79.5 in the continuous sense. In the continuous sense, right? In order to capture 80, and keep getting bigger and bigger, in order to make sure 80 is part of my solution, I got to go a little bit left of that value to make sure that's actually captured. So I'm subtracting 0.5 from 80 to make my left most bound in the continuous sense start at 79.5. Okay, so again, this is a brief overview of the Chapter 5 material. Make sure you go back through and read the textbook, go through those reading guides, the notes that I have uploaded, some of the example videos provided by the publisher I think are excellent review videos. Help yourself get ready for the test here. We'll see you later, guys.